Hello, my name is Avi Kantha, and today I will be discussing my lab 4 oscillations for Physics 2211. For some introduction, this line will aim to show the observed motion of a mass that is attached to a spring and is oscillating to see whether the model we created follows the energy principle. The object will be observed as a mass, observed motion will be using tracker, and the predicted motion will be seen using globe script. The lab will help us understand the energy principle in detail, which talks about how energy is never created nor destroyed, only transferred. Meaning if everything is accounted for, the total energy will be zero. System's mass, spring, and earth, surroundings is none. So some important equations we have is Newton's second law, which is F net is equal to delta P, momentum over delta T. And in this case, there's only this force of spring and force of gravity, and those are the respective equations plugged into F net. The energy principle, we have the total system energy is equal to the work done by surroundings plus Q, and the system is the mass, spring, and earth, and there's no surroundings. That means the energy system should just be zero. And the energy system will become with kinetic energy, the spring potential energy, and spring gravity, which will be equal to zero. And some other important equations will be the velocity update formula, position update formula, the kinetic energy formula, the potential energy through gravity formula, the potential energy through spring formula. So this is a little preview of the results we'll have. So this is our observed motion that we got using trackers. So we put our video in and set the video length, inserted axes, inserted calibration stick, and then we plotted points to different intervals, and then observed table and graph. So this table is just a short depiction of what some results we got. There is many more points up until 9.5 seconds, and this is the graph that we got. As you can see, it's like an oscillating like sinusoidal graph for both the x and y axes. So some tracker findings. So this is given to us the object mass and the stretch length, which is the 0.402 and 0.70. Initial position was our first point that we plotted up here, which is negative 0.124, negative 0.642, and 0. And initial velocity is, of course, 0 as we're starting from rest. All these findings were necessary for closed model, and there's a little bit more tracker findings as we used our intervals through the time in order to find our oscillation period. And with the oscillation period, we can plug it in to that oscillation period formula to find our K, which is our spring stiffness, and then we use that spring stiffness to find our lax length using our F net formula. And this is our globe script code. So we plugged in our ball mass, the initial position, initial velocity. We plugged in our gravitational constant, our spring constant that we found in this slide, and our L and our initial length, which we found in this slide also. Then we plugged in some equations to find L hat spring, kinetic energy, potential energy gravity, potential energy spring, and total energy from the formulas we showed earlier. And then we did our while loop, which is basically showing the different intervals of the change in energy. So we basically used the previous energy, set it at the initial, and then we did a bunch of the formulas we did again, like we used our F net and whatnot, and we kept going until we went back and we found our kinetic energy, potential energy, spring energy, and new energy using our new position, new velocity, and next point. And then we subtracted using the old point to find our old mass, our old energy and energies, and our old energies. So this is the graph that we got after we put everything in. So the blue is the model, and the green and the red's the experiment. As you can see, the models have a higher peak in the x direction, but a lower peak on the y direction. And a lot of these errors could be accounted for outside forces, such as air resistance, which might have slowed the mass down over time, meaning there's likely work done by surroundings. And there might be some slight errors in measurements, like taken from the video. For example, the length of L might be slightly inaccurate, leading to different results. And point plotting, some of the points may have not been placed completely accurately, and hence changing the results. So what does it mean? And for this scenario, for your model system, is the energy principle satisfied? So that's why I answered by briefly discussing your plots of energy changes. So we got this graph when we plugged it in through the model, and it shows the different changes in energy throughout the time. However, one thing you can see is that at the 0 point on the y-axis, there is a delta E, which is almost always right at 0. So that means this spring mass system justifies the energy principle. And then we want to compare the x direction and y direction and see if we get different k values for them, and we want to discuss it. So as you can see in the x direction, we got a k value of 5.8, and the y direction we got a k value of 6.8. As you can see, that are different, and they'll give you different results in the actual model. And I believe the reason for this might be the air resistance, as it may be pushing more towards the x direction, hence making the oscillation times bigger, and it'll lower the k value. Thank you for listening to my presentation on Lab 4 for Physics 2211.